So let me begin with the first introduction because I think just now the introduction given by Vina is a bit too informal. So I give a more formal introduction about myself. Okay, so I'm Kheng Meng. So my job is actually as an embedded security researcher. I work at CSIT. So if you don't know, CSIT is actually a technical agency under Ministry of Defense. Okay, so I worked for about 10 years. I work in private and public companies. So what I do is I do hardware design, I do microcontroller firmware, and I do embedded Linux, which I'm sure is very different from what most of you here do. I'm probably the one now. Okay. Okay. So okay, let me dive right in. So what is embedded Swift? So embedded Swift is something that was actually announced in the WWDC last year. Okay, so it's radically different from the Swift that I'm sure most of you use it. For example, I think most of you use it either for macOS or iOS apps, right? So embedded Swift is actually for resource-constrained microcontrollers. So examples would be like ESP32, Raspberry Pi Pico, and STM32. Okay, so what is the difference, the general difference between embedded Swift and what came before that? So before embedded Swift, right, most of you, when you use Swift, you use it for iOS, macOS, even Linux and Windows. So the thing about all these platforms is that the hardware is quite powerful. So we are talking about gigahertz class multi-core CPUs, gigabytes of RAM, gigabytes to terabytes of storage. But when it comes to the embedded world, right, it's actually several magnitudes apart. So in the embedded world, we are talking about bare metal microcontrollers, or MCU for short, where there is no operating system or a relatively small real-time operating system. In terms of performance, we are talking about megahertz class single core or dual core CPUs. RAM is measured in kilobytes to megabytes. Storage is also measured in kilobytes to megabytes. Definitely very small. Okay, so because of this, what's the difference, right? So embedded Swift actually is still experimental as of today, even though it was like announced last year. Last I checked a few weeks ago, it was still experimental. So basically, Apple hasn't officially released it yet. Okay, it's a subset of conventional Swift. So, on the basic summary, no foundation. Can you imagine that? No foundation. Then no print and string floating point support. Okay, the Xcode ID does not support embedded Swift. Can you imagine coding Swift without Xcode? Okay, in fact they have I just took a screenshot from their website. They have so many things not available, not available, not available. So many things. Okay. Okay, so if you you may use bridging headers like to call objective C code. So in embedded Swift, this bridging header can only import C code. There's no support for Objective C. For the full list of what is not available, you can just go and check out the website. Okay, so these are the topics I'll go through for this presentation. I'll talk about the hardware. I'll talk about running embedded Swift example directly from Apple's GitHub. And then how to communicate with the environmental sensor. Okay, then how I use LMs to help me in this project and what are the challenges I encountered. And finally, I'll talk about my personal conclusion on embedded Swift. Okay, so the first thing when it comes to embedded is to select the board. Okay, to select the type of microcontrollers. Okay, so there are only a few microcontrollers supported by embedded Swift. So the way to find which MCUs are supported, you just go to the website, to the repo, look at the examples, and then you see which in the list is supported. Okay, it's actually not a lot. Okay, so the list that is supported are the Expressive ESP32-C6, Pi Pico 1 and 2, Nordic NRF52, and STM32, specifically these models only. Okay, so why did I select this one, ESP32-C6 DevKit C1? Is because okay, it's relatively cheap with $15. There is something else that's even cheaper, which is the Pi Pico, which is $6. However, it is very difficult for development because you need to do a lot of button pressing, and then to do proper development, you need to buy another debug probe, which is $20. So it's no point. In the end, it will cost more. So I chose the ESP32. Okay, so more about this board. So this design was created by Expressive Systems. Okay, so Expressive Systems is actually a China company, but the CEO is from Singapore. Okay, then it's using this module called ESP32-C6 Room 1. Okay, it has an onboard RGB LED. Okay, then it has two USB-C ports. So one of the USB-C ports is what we call a native serial port. Another one is a USB UART serial port. Okay, not so relevant. Okay, just an example. So what's inside this board? So this board, okay, it uses this module, ESP32-C6 Room 1. So inside this module is this chip. It's called ESP32-C6. Okay, so this the specs for this MCU is the flash you can see is only a few megabytes only. It's quite small. Then the microcontroller specs you can see is only a dual core CPU in what 20 megahertz up to 160 megahertz. The RAM is measured in kilobytes. Okay, it has Wi-Fi and Bluetooth and a bunch of other connectivity peripherals. Okay, so the first thing when it comes to using any language is like you would use something like Hello World example, right? Okay, so the Hello World equivalent in MCU world is to blink the LED. Okay, so Apple has provided an example code of how to blink a light strip made up of WS212 RGB LED. So all this. Okay, so the objective of this example is to cycle through the different colors. Okay, and then is to help you get started easily. Okay, so let's get started. Okay, so in their example, right, what they recommend is that you have to install a nightly version of Swift because this is experimental. So the stable version of Swift does not come with the embedded Swift support by default. Okay, so to install this nightly version, right, you have to install something called a main snapshot, and they also recognize that you have a multiple Swift toolchains, so you use a Swiftly tool to help manage these multiple toolchains. Okay, so we can see that. Let me just run Swiftly list. Okay, so you can see that by default I have 612, but 612 by default doesn't have the embedded Swift support, so I have to install the toolchains, and then after that I switch to it. Okay, then after that, right, we need to install the manufacturer's, in this case Espressive's toolchain. So I'll clone their Espressive repo. Okay, so the embedded Swift cannot work standalone. It requires the interacting with the manufacturer's toolchain. Okay, so in the interest of time, of course, I pre-installed all the toolchains already. So now after installing all the toolchains, we want to run the example from Apple, okay, which is the ESP32 LED strip SDK project. So I already have this project here. Okay, so this I have to slightly modify this project because the project by default cannot be run on my board. Okay, the reason why is that the Apple's example requires a light strip, but I don't have a light strip. I only have one LED that is running on the board, so I cannot use the example as is. So just do a slight modification. The original example assumes that you have 8 LEDs, and then it assumes a certain pin that the MCU talks to the LED. So I just change it to 1, then change to pin 8. Okay, so MCU, how do I know it's pin 8? I have to actually go to the schematic. Okay, schematic is basically the electrical drawing on the MCU, and then it says here that, okay, this one goes to GPIO 8. Of course, it's also written here, but we need to double confirm that based on schematic GPIO 8. Okay, I modify the example. After that, I will compile the example. Okay, so to compile the example, okay, the first thing we have to do is to enable the manufacturer's IDF environment. Okay, so after I do that, right, okay, then I need to tell the IDF that, okay, I want to compile for this particular compile target, which is a ESP32-C6 chip. Okay, then after that I will build. Okay, this will take some time. Okay, so once I build, okay, now I'll attempt to flash the firmware over to the board. Okay, so now I flashed it already. Let's monitor the serial UART. Okay, so on the serial UART, you can see that hello from Swift ESP32-C6 using this on IO8, which is actually this one. Okay, so this proves that I've compiled this particular project and I flashed it in, and then the LED is flashing here. Okay. Okay, so that project is a bit too simple. Let's do something more complicated. Okay, So in real life, of course, the MCU is not going to be just flashing LEDs. It's too simple already. So in real life, most embedded projects, you'll be talking to some sensor. So in this example, I'll be talking to a sensor from made by Bosch called the Bosch BME680. This sensor has 4 functions: temperature, pressure, humidity, and gas. Okay, this sensor is quite small. It's actually over here. Okay, if you can't see the board, basically this is the sensor. Okay. Okay, this sensor is only this size, but then of course I can't use the sensor as is. So I bought a breakout board basically to break out all the pins of the sensor to be allowed to be placed on the breadboard. Okay, in case you don't know, this whole thing is a breadboard. Okay, so how this sensor is able to talk to the MCU is based on a bus called I2C, or short for Integrated Circuit Bus. Okay, it's an electronic bus where a master, in this case, which is the ESP32, can talk to one or many slaves. But in this example, I only have one slave, which is the sensor. Okay, so it has 2 data lines, one data line and 1 clock line. Okay, the typical speed of such a bus is really quite slow, 100 to 400 kilobytes per second only. Okay, so now with AI being hot, right? First thing I do is let's ask the LM. So in this project I use ChatGPT, Claude, and Copilot. Okay, the first thing I realized is that all these LMs cannot generate me satisfactory Swift code. I mean, it generates some Swift code, but then it doesn't work. Okay, so these are the basic observations. Most of the code that it generated, I realized, is targeted for iOS or macOS. Okay, so I mean, it's pretty obvious because most of the code online is for iOS and macOS. Embedded Swift is super niche. Okay, or sometimes they cannot. They just provide empty functions, say go and fill it. Okay, another problem I see that it hallucinates some non-existent functions. Okay, which I'm sure all of you have faced. Okay, so these couple of reasons, Embedded Swift is pretty new, only last year, still experimental. Okay, most of the code is for iOS and macOS. And there are no official Apple examples for Embedded Swift ESP32 I2C communication, this specific thing. So I think that's why the LA doesn't know how to do it. Okay, and another thing is embedded code in general is quite niche. So with very little code online, and whatever embedded code online is mostly C and C++, it's not Swift. Okay, so how do I address this problem? So the first thing is like I can write the wrapper code. Like you want to interface with the sensor, most of the code is in C, I write in C. Okay, then I avoid all the unsafe code and C test structures. I put in C, then I just call from Swift. This strategy is suggested by ChatGPT. Throw all the code into C. Then only use your Swift code to go and call the C code. Okay, because after I asked you to keep coming out, then you give up already. Okay, then this third point is something that I thought of, is like, once I have the C code, right, why not translate it to Swift, which is more proper, right, so that we can see whether Swift can still do it or not. Okay, so before we go to coding, right, we first have to understand how this communication works. So in embedded world, right, we use data sheets a lot. Okay, we need to know how is the microcontroller going to communicate with what kind of protocol, what kind of things you need to send. And this goes down to very low level, goes down to the byte level. Okay, so in I2C, master always initiates the communication. Then data transfer usually work on register level. So we have to send this byte. The master write the slave address. So every I2C device has a unique I2C address. We write the slave address, write the register address, in the byte write the data, then send the stop. Let's say you want to read data, we write the slave address, we write the register address, we stop, then the slave will reply back. Okay, so we need to do in this specific order. Okay, so now with this, right, how do we go to structure this code? In what form, in what architecture? Okay, so for the most embedded sensors, right, manufacturers, like in this case Bosch, they usually provide a library, a driver library. Okay, so the driver library is something like in this form. They'll give you the C header file. No, it's a C library. They say, okay, you can initialize this, you call this library to get the data. After that, then you get the data from the library. But the problem is the library has no visibility on which MCU are you using it on. So it's not able to like talk directly to the MCU, because different MCUs have different ways of addressing the bus. Okay, so what they normally do is that they will ask you to provide a function pointer of how to read and write to the I2C bus, which is something like this. This is the header of the the definition for the declaration for a function pointer, and they also want you to provide a way to delay how many microseconds you want to delay. It's a delay function. Okay. Then on the other side, you have the ESP, in this case expresses board support package. So most microcontrollers, they give you a board support package. Okay, so basically it's something like the API to use the functions of the MCU. So in for the relevant functions in this MCU, I have the I2C master transmit receive, master multi-buffer transmit, and the delay function. So as a job of an embedded engineer, you need to find a way, right, to bridge these two together. Okay, so you need to find a way to let the library able to talk to the BSP function of the MCU. Okay. Then after that, you can call the library, and the library will call your MCU functions. Okay, so let's go a bit further. What about the compilation process? Okay, so in Swift, right, we use a SwiftC compiler. The SwiftC compiler, you compile the Swift code, you get an object file. Okay. For the MCU side, the native C code, you use the toolchain provided by the manufacturer. In this case, a RISC-V GNU toolchain, so you get a C object code. Okay. In this example, after that, right, you will call the toolchain and the BSP. You combine everything into one binary. Okay. So actually, the Swift code and the C code, right, it compile to say object code is indistinguishable to the toolchain. They look the same. Okay, so now let me do a demo of the C wrapper. Okay, so I wrote a C wrapper for this. Let me go to that project. Oh, sorry. Okay, so we do the same thing again. We will set the target to this. Okay, then after that, we will build. Okay, so technically for the ESP-IDF, you can call the flash, and then it will just call the build for you automatically. But I just completeness, I'll do the proper step. Okay, so we can see that now is the MCU is reading data from the sensor and then displaying over the serial port. Okay, you can see the data live. So to prove that this is working, right, let me blow it to the sensor. Then you see the values change. You can see the humidity goes up, right? Yeah. Okay, so let me stop this one. Okay, so how does this work, right? Okay, so in this example, right, I will follow the strategy suggested by ChatGPT. I write everything in C first. The only thing the Swift code does is to call the C code. Okay, so yeah, okay, let me go to the example. Okay, so this is the main Swift code lah. Basically the top level. All it does is it calls something like this and something like this to get the data. Okay, so this and this is actually functions inside my wrapper. Okay, you can tell that this entire wrapper is written in C. Okay, here and the get data. Okay. Okay. So in the interest of time, I will not go through everything. I just go through the more important one. Basically, it's the function pointer. Okay, these are the 3 function pointers which I need to pass to the BME680 library. Okay, so that it's able to talk to the sensor using the I2C functions of the BSP. Okay, so you can see that what this function does. Okay, so the BME680 library says that I need a way to read the I2C registers, right? Okay, so implement this. Okay, so I will call directly. It just happens that the function parameters are exactly the same, so it's easy for me in this case. I just pass through the parameters directly to the ESP BSP for master transmit receive. Okay, the problem is for the right one. The right one is not a direct pass through, so I had to do some adjustment. I had to create an array. After that, then I pass the array over to the ESP BSP. Okay, as for the delay function, thankfully it's also just a pass through. There's a native delay function for ESP BSP. So after that, then my Swift code, which is on the right side, you will just call this directly. I have a function basically just to get the data. I just return everything back. Then on the Swift side, right, I just print out everything. Okay, so the Swift side is basically not doing much. Okay, in this case, and also remember, just recall just now I say that the embedded Swift cannot do printing for floating point, right? So in this case, I will outsource that ability to the C side, the wrapper side. So I send the float value back to the wrapper, and all it does is printf this using this on the C side, because the Swift cannot do it. Okay. Okay. So yeah. So that was the example. Okay. So there are some some extra stuff when it comes to interacting between Swift and C, which is you need to map certain types. So in C, right, this is a very low level memory pointers access. So Swift doesn't really like it, but they still let you do it. So they call it, whenever it comes to dealing with C pointers, they call it unsafe pointer. Unsafe mutable pointer. Wait, unsafe pointer means cannot change. Unsafe mutable pointer means can change. Okay? Then you have raw pointer, unsafe everything. It's like as if they're trying to tell you that please don't use it. Okay? Then it also says that C macros cannot be imported in Swift because Swift doesn't have such a function. Such an ability. Okay, so with that in mind, right, now I come to the third part, which is I want to translate whatever the wrapper stuff I did into from here into Swift, because so at least that's more learning value, right? If I just get a Swift to call the C code, then what's the point, right? Right. So I did another project here. Basically, I translated whatever you see it in this wrapper thing, right, into here. Okay. So all into Swift code. I do a basic scroll through, you can tell that everything's in Swift. Okay, but it's not that straightforward. Okay, given the limitations that I mentioned in the previous slide. Okay. Oh, I think it's a bit too small. Okay. Okay, then let me go to this one. Okay, so this is in the original C parameters, right? You can see this. So notice how I try to translate. Let me go to this. You can see unsafe mutable pointer, unsafe mutable pointer. Then all the false unwrap. Wow, this I did use the AI to help me a bit, but it made a bit of some mistakes. Okay, so if you're not very sure, you can see from here. So in Apple, they have this side here. They tell you what is the translation between the two types. Okay, so after that, yeah, I did the translation here. Okay, I had two parts. Let me comment this thing. Okay, so my initial attempt to translate the array was this. So I had to do initialization, then after that allocate it. This is actually done on the heap. Okay, in the C side, right, I didn't have to. You see, I just allocate this on the stack. Then I just send the array to the C functions. But in the originally when I first did the unsafe mutable pointer, right, I realized that you have to do it. Okay, that was my initial assumption. Okay. Okay, so like I said, unsafe mutable pointers allocated on the heap because you need to deallocate. So that's the first sign that it's allocated heap. Now the problem is, right, we all know that heap allocation is something you should try to avoid if you can. You should try to allocate on the stack whenever feasible. And this is especially bad on microcontrollers because microcontrollers are very slow in allocating memory. And repeated allocating and deallocating will cause memory fragmentation. Okay? And there's a possibility that it might not even allocate at all, just return you fail. Okay? So I asked AI, can you give me an example of how can I do this, create this unsafe mutable pointer without a heap? Okay, so I have to thank the AI. AI actually gave me this answer. So it said that you can use something like a with unsafe mutable pointer. Okay, so after that you mutate the pointer mutate the pointer into a mutable form. Okay, so I'll show you the example. Sorry, is it this one? Okay, it's here. Okay, let me scroll. Okay, so before that, I had, remember, you see I had to allocate, initialize, initialize, after that deinitialize, deallocate, right? Yeah, this is quite bad, it's on the heap. On here, you don't see that at all. There's no initialize or deallocate or what. So everything's on the heap. So with this, right, this closure over here, you can actually temporarily able to use the unsafe mutable pointer only within the context of this closure. Yeah. Yeah, this something seems, yeah, correct. Then after that, I just call the ESP BSP directly. Okay, so this is the heapless option. Okay, so let's do an example. See, here we go. Okay, so this example here is a Swift wrapper, the one without any C code at all. So this is done completely in Swift, except for calling the ESP BSP. Okay, so everything works now. So basically I did the translation properly. Okay, so there are some challenges I encountered with this project lah. So the code that initially generated by the LLMs actually has some issues lah. So when it comes to troubleshooting on embedded, it's a bit difficult lah. Okay, so one of the ways is actually I had to use a logic analyzer. So in case you do not know, a logic analyzer is basically a special electronic tool over here that will let you visualize the digital signals that is tapping on. Okay, so after that, you see, you visualize the raw waveforms, right? Then you can tell whether are you sending correctly, because it's not like your S code IDE where you probably can do step through, right? You can't do it. Okay, it may work if I'm doing a pure C code, but remember this, I'm doing Swift and C at the same time, so there's no automatic debugging tool that can cross both languages. So this is the only way actually to troubleshoot this. Okay, so the conclusion, actually I have a lot of points there. Okay, so embedded Swift is still experimental after 1 year. So automatically what it means is that you probably shouldn't be using this in production now, because it means Apple can change anything anytime, as long as something is not stable yet. Okay, then what I feel after going through this, right, is that there is a significant mismatch between the goals of Swift or all high-level languages versus the goals of typical embedded platforms. Because of high-level languages, you are generally discouraged from using low-level features like UnsafePointer. The fact that Apple have to call it UnsafePointer is an indication to you already. You probably want to avoid using that, right? But in embedded world, you realize I have no choice, I must use. It's actually an often thing that embedded engineers have to use low-level access because we need to have the performance and memory optimizations given the very relatively lousy specifications of embedded platforms. Okay, embedded devices are not as vertically integrated, unlike macOS and iOS, where Apple controls everything from the CPU up. But on embedded world, right, Apple does not control the microcontroller vendor. Okay, and the microcontroller vendor, they only provide you the SDK and almost always C libraries. Okay, there are not many MCUs available supported, so you saw only ESP32, R5, Pico, STM32. Okay, most embedded stuff you see almost everything are in C or C++. That includes the SDK and the debugging tools and the documentation. So it means that it is once you throw another language into the mix like Swift, it's going to make your debugging very, very difficult. So my final conclusion is it will be very challenging, I don't want to say cannot, for Apple to get MCU and embedded engineers to adopt Swift, at least in its current form. Yeah, okay, that's all. Thanks.
Thank you so much. Some of you are still alive, right? Yeah, all of you. Okay.
Any questions or later?
I will just take one question if there's any.
Yes.
Actually, why do you think that Apple is trying to experiment embedded devices?
Wow, this is probably something you must ask Apple. You can't ask me. Okay.
Arduino also, so
Okay.
yeah.
if I were to guess,
Yeah.
okay, if they can push more people to use their platforms, then it's even better, lah. Right? It's like, okay, example, why did Apple also support Windows and Linux? Remember, obviously it started off with only Mac OS and iOS, right? Why did they support more? So it's to get more people on the ecosystem, and if more people use it, then it's better. And also, I think another possibility is that some people may be turned off by C. Then if let's say you are come from the Apple ecosystem, right, you're familiar with Swift, right, then maybe it's easier for you to do embedded stuff now. Maybe, I don't know.
Are you satisfied? Okay, good. You can chat with him again after the talk, the second talk's end. Okay. So yeah, thanks Kheng Meng. The talk is very interesting. However, I thought MCU is Marvel Cinematic Universe. Yeah. So